we've seen that if you have a limit that gives you 0 over 0 or infinity over infinity, then you can use L'Hopital's rule to evaluate that limit. But actually, L'Hopital's rule can be used to evaluate other situations as well. So let's have a look at a couple examples of that. So here's one. We're going to evaluate the limit as x goes to 0 from the right of x times natural log of x. And if you try just plugging in the 0, I'll put air quotes around that, really we're taking the limit of each piece as x goes to 0 from the right. Well, the x, as x goes to 0 from the right, x gives you 0. And as x goes to 0 from the right, natural log of x gives you, well, natural log of x goes to minus infinity. So 0 times minus infinity, well, on the one hand, the 0 is trying to make this product small, close to 0, and the minus infinity is trying to make this product big, that is close to negative infinity. And without more information, other than just 0 times negative infinity, it's impossible to know which one of these influences wins out. So we can't tell if this goes to 0 or goes to minus infinity or maybe something in between. It's impossible to say. This kind of situation where you have an expression where you actually can't know what it evaluates to, this is called an indeterminate form. I'll abbreviate that, an indeterminate form. And we've actually seen a couple indeterminate forms before. The two that we've already looked at for L'Hopital's rule are 0 over 0 and infinity over infinity. Now it's tempting to think, because this is an indeterminate form, we could do a L'Hopital's rule-like calculation with it. So it's tempting to think that if the limit as x goes to 0 from the right of x times natural log of x, shouldn't that be equal to, I'll put a question mark on this equals, shouldn't that be equal to the limit as x goes to 0 from the right of the derivative of x times the derivative of natural log. This is sort of a L'Hopital's rule type thing, but for a product instead of for a quotient. Let's see what this would give us. This is the limit as x goes to 0 from the right of derivative of x is 1, derivative of natural log x is 1 over x, and this is, as x goes to 0 from the right, 1 over x goes to infinity, and so this is actually plus infinity. Okay, but we'll see that this idea of just using a L'Hopital's rule type thing, but for products, is actually wrong. So this whole thing is wrong. Okay. We guessed that maybe we could do a L'Hopital's rule type thing on the product, but this actually doesn't work, as we'll see. L'Hopital's rule only applies to these two indeterminate forms, 0 over 0 or infinity over infinity. So to evaluate this limit, we have to rewrite the thing that we're taking the limit of, x times natural log x, so that it's a quotient. We can only use L'Hopital's rule if we have a quotient. So let's start over. And I've messed up my brush size. Let's start over and find the limit as x goes to 0 from the right of x times natural log of x. Okay, we have to write this as a quotient so that we get 0 over 0 or infinity over infinity. Those are the only indeterminate forms that we can use L'Hopital's rule on. So to do that, so we're going to get limit as x goes to 0 from the right. Our options are take this x and shuffle it into the denominator, or take this natural log and shuffle it into the denominator. We're going to either get x over 1 over natural log x, or our other option is natural log x over 1 over x. Okay, you can see in the first case, the indeterminate form that we would get is 0 over 0. And in the second case, the indeterminate form we would get is minus infinity over plus infinity. Both of those are indeterminate forms where L'Hopital's rule is available. But it looks like the second one is going to be easier to differentiate. So just to make it easier on ourselves, let's use the second one. So we get limit as x goes to 0 from the right of natural log x over 1 over x. Okay, so 1 over x is the same as x. So these two things that we're taking the limit of really are the same. All right. Just to verify, if we sort of naively take the limit as x goes to 0 from the right, the numerator here, natural log x, goes to minus infinity. The denominator here, 1 over x, as x goes to 0 from the right, goes to plus infinity. And so we're in an infinity over infinity type indeterminate form. And that is one of the situations where we can use L'Hopital's rule. So using L'Hopital's rule, we get the limit as x goes to 0 from the right of, okay, so remember how L'Hopital's rule works. You take the derivative of the numerator. Now we're not doing the quotient rule. We aren't taking the derivative of the whole thing. We're using L'Hopital's rule, which says take the derivative of the numerator and denominator separately. So derivative of natural log x is 1 over x. And derivative of 1 over x, well, remember 1 over x is really x to the minus first. And the derivative of x to the minus first is minus x to the minus second. All right. So this is the limit that we have to evaluate now. It's kind of tempting to immediately check to see what happens when you take the naive limit by sort of plugging in 0 here. But you get infinity over minus infinity. So you're still in an indeterminate form kind of situation. But before you try to calculate the limit again, simplify this expression that we're going to take the limit of. So this is not using L'Hopital's rule. This is just doing algebra to simplify this expression. And you can see why we should simplify this expression. We get 1 over x. This x to the minus second, that's really times x squared in the numerator. Don't forget this minus sign. There's a minus sign out front. And when we finish simplifying this expression, limit as x goes to 0 from the right, it's just minus x. And we can take the limit of that. It's as x goes to 0, minus x is just 0. So this entire limit, it's just 0. You can see that this is different than what we would have gotten using our first attempt, which is wrong, right? Our first attempt, where we were kind of guessing on how to do it, our first attempt gave us infinity. But now we see that actually this limit should be 0. Okay? So, moral of the story here is if you have an indeterminate form that is a product, the 0 times infinity indeterminate form, rewrite your product as a quotient so that you get 0 over 0 or infinity over infinity, and then use L'Hopital's rule on the resulting quotient indeterminate form. All right. Let's look at another example. So here we're going to evaluate the limit as x goes to 0 of cotangent x minus 1 over x. Now again, this, if you sort of calculate this limit naively by just kind of plugging in 0, cotangent of 0, actually cotangent of 0 isn't defined, and it's sort of plus or maybe minus infinity. It depends on which side you approach 0 from. And 1 over x is actually also plus or minus infinity, depending on which side you approach 0 from. And so the difference is either infinity minus infinity or negative infinity minus negative infinity. Either way, whether it's plus and plus or minus and minus, either way this indeterminate form is, or this expression is indeterminate, because if it's plus infinity minus plus infinity, well, which infinity wins? The one that's trying to make it positive or the one that's trying to make it negative? we can't say without knowing something more. So this is an indeterminate form. Just like with the product indeterminate form that we saw a minute ago, you can't actually directly use any sort of L'Hopital's rule kind of rule of thumb here. L'Hopital's rule only applies to the two quotient indeterminate forms, 0 over 0 and infinity over infinity. So before we make any progress on evaluating this limit, we have to write this as a quotient. We don't have any option. So let's see how we could do that. Limit as x goes to 0 of cotangent x minus 1 over x. So to write this as a quotient, let's see, we're going to have to do some sort of algebra. 1 over x is already a quotient. So maybe we could just put these over a common denominator. That would express the whole thing as a quotient. And if we're going to write everything as a quotient, well, cotangent is actually also a quotient. Cotangent is cosine x over sine x. So let's put these two things over a common denominator because we are subtracting them. So this is the limit as x goes to 0 of x times cosine x minus sine x over, the denominator is going to be x sine x. Okay, quick check just to make sure we're getting an indeterminate form here. As x goes to 0, this first part of the numerator is going to give us 0 because of the x. The second part of the numerator is also going to give us 0 because sine of 0 is 0. So in the numerator, we just get 0. And in the denominator, as x goes to 0, we get 0 times sine of 0, that's 0. All right. So now we're in a situation where we have a quotient indeterminate form 0 over 0. So now we can use L'Hopital's rule. All right, so we get the limit as x goes to 0 of, and as usual for L'Hopital's rule, differentiate the numerator and differentiate the denominator. So in the numerator, we have to do a product rule here. Derivative of x cosine x is cosine x minus x sine x minus, and now we need to take the derivative of sine x, that's cosine x. And then in the denominator, derivative of x sine x, that is sine x plus x times cosine x. So there I've used the product rule to find that derivative. All right, now before we try to evaluate this limit, we should simplify it. And you can see there are a couple things that simplify. There's a minus and a plus cosine right here. Okay. Now in the denominator, we get, so limit as x goes to 0, sorry, in the numerator, x times sine x, that's 0 still. Sorry, I need this over here. In the numerator, we're still getting 0. And in the denominator, 0 plus 0, well, we still get 0. So even after simplifying, we're still in a situation where we have an indeterminate form. That's okay. We can use L'Hopital's rule again. So take the derivative of the numerator. We get our minus sign out in front. And then let's do our quotient rule. So sine x minus x cosine x in the numerator. And then in the denominator, derivative of sine is cosine x plus, and now we have to do the quotient rule again, cosine x plus, sorry, that's going to be a minus, x times sine x. So there's our quotient after the second round of L'Hopital's rule. And it doesn't look like anything simplifies. We could combine these two factors of cosine, but nothing is going to cancel. So Now let's try evaluating at 0. In the numerator, we get minus sine of 0 is 0, minus 0 times cosine of 0 is 0, over, in the denominator, cosine of 0 is 1, plus cosine of 0 is 1, minus 0. So the whole thing turns out to be 0. All right, so in this situation, we had an indeterminate form that was infinity minus infinity, or negative infinity plus infinity, which amounts to the same thing. That's an indeterminate form because you can't tell whether the positive or the negative infinity wins when you add them together. So to handle this, we converted it into a quotient by putting it over a common denominator. And that quotient gave us a 0 over 0 indeterminate form, so we were able to use L'Hopital's rule. We had to use L'Hopital's rule twice this time before we got a limit that we could actually evaluate. I should mention that there's no guarantee that if you keep getting indeterminate forms, that using L'Hopital's rule over and over again will always give you a result at some point. It's possible that you just keep getting indeterminate forms forever. But in most situations, using L'Hopital's rule a few times will give you a value for your limit.